Hello everyone, my name is Singhi Choi from the MMAI lab at Hanyang University. Today I will be presenting our paper Follow the Saliency. Let me start by briefly introducing the task. Dense video captioning, or DVC, aims to detect multiple events in the long untrimmed videos and generate a natural language caption for each event. Unlike standard video captioning, DVC must answer both when an event occurs and what is happening simultaneously. Now, why do we bring in a retrieval? Retrieval provides semantic evidence by supplying the decoder with relevant captions from external data store. Retrieved captions help the decoder produce richer, more accurate descriptions. But here's the key point. Retrieval quality entirely depends on the quality of the input segments. Here is the overall pipeline. A video segment queries the data store, retrieved captions are combined with the visual features, and the decoder produces the final output. Simple and intuitive, but the segment is the bottleneck. Two representative prior methods are HiSim2, which uses uniform sampling, and CVPR, which uses the heuristic similarity-based segmentation. Both achieve strong results, but both share a fundamental weakness. Their segments are not aligned with the grand truth event boundaries. Wrong segments lead to wrong retrieval. Boundary mismatch causes no retrieval, which delivers incorrect semantic evidence to the decoder. This is the core problem we set out to solve. And this chart confirms it empirically. As segment quality improves from CVPR to ours, all captioning metrics consistently rise. The relationship is clear and strong. Better segment, better retrieval, better captions. So, how can we obtain GTL line segments beyond heuristics? This is the core question we aim to answer. Our answer is this: learn supervised saliency for GTL line segmentation and then reuse that salience signal for both retrieval and caption generation. We call this framework STARK. Now, let's walk through the method. STARK has two core components. The first is supervised salience training, which learns frame-level importance directly from GTL annotations. The second is a unified salience-based design, which applies the single salience signal to both retrieval and generation. On the visual side, input frames are encoded by spatial encoder and temporal encoders, producing a frame-level visual representations. On the text side, speech transcriptions are encoded and provided as additional input to the decoder. This allows the model to leverage both visual and linguistic context. Before salience prediction, we apply SWSA, sliding window self-attention. This model refines temporal features by capturing local context across neighboring frames using multiple window sizes. Importantly, it has no low-level projections, making it lightweight and parameter-free. For training levels, we convert existing DVC ground truth timestamps in binary level highlight levels. Frames within event boundaries are labeled 1, the rest are labeled 0. No extra annotation is required. The highlight detection model takes refined local features and a global video summary via attention plane and predicts a salience score for each frame. The training goal is straightforward. We want the model to assign higher probability to GT highlight frames. We use a list-wise softmax cross-entropy loss. The model learns to concentrate probability on annotated event frames, while implicitly down-weighting background frames. Now, what does the model actually learn? As you can see from these visualizations, salience scores are consistently higher within ground truth event regions and lower in background frames across multiple different videos. This single supervised salience signal is then reused to guide both retrieval and generation throughout the entire framework. The highlight detection module outputs salience scores which feed into our unified salience-based design. The first component is SGSR, Salience Guided Segmentation and Retrieval, which answers where to retrieve. Higher salience means is your assignment to a segment. The second component is SALIP, Salience Prompt, which answers what to generate by providing explicit salience cues to the decoder. In SGSR, salience scores are normalized via sigmoid to form a salience prior distribution over frames. This distribution will guide how frames are assigned to segments. We apply optimal transport-based clustering. Frames are self-assigned to k-linear anchors through a transport plan. Each anchor represents a semantic prototype for a video event. Saliency is incorporated in two ways. First, as a bias term into the cost matrix, high saliency reduces the assignment cost. Second, as a soft constraint on the frame marginal, encouraging salient frames to receive more transport mass. The key insight is this. High saliency, low cost is your anchor assignment. Salient frames naturally cluster into meaningful event-aligned segments. We score our segments by semantic alignment and temporal stability, select the top k segments, and retrieve the most relevant captions from the data store. Qualitatively, our salience-guided segments align closely with GT events boundaries, while uniform and adaptive baseline are frequently misaligned. The retrieved captions are also semantically more relevant to the actual video content. Now for the second component, salib. Salience scores are projected through a learnable mapping layer to produce salient prompts. These prompts, along with refined visual features, retrieved captions, and text features, are concatenated to form the full decoder input. SGSR provides the retrieval embeddings, and salib provides explicit salience cues. Both are derived from the same supervised salience signal, ensuring consistent temporal grounding across retrieval and generation. Salib explicitly tells the decoder what to focus on, salience event-relevant frames during caption generation. The concatenated input is passed through a TF-based text encoder, which outputs event timestamps and their corresponding captions. The total training loss combines the cross-entropy captioning loss with the salience loss. These two losses jointly optimize both captioning quality and salience alignment. To summarize the method, Stark combines supervised salience training with a unified salience-based design. Better segments, better captions. Now, let's look at the results. Stark achieves state-of-the-art performance on both UCOOC2 and VITT benchmarks, outperforming the previous best method, Supervised, by a clear margin. For event localization as well, Stark achieves top performance on both benchmarks. The ovulation study confirms that SGSR and salib are complementary. Each model alone brings a meaningful gain, and combining both achieves the best performance. The salib ablation is particularly telling. Replacing our prompt with a Gaussian noise or zero prompt both degrade performance significantly, confirming that accurate salience cues are essential, not just setting external tokens. And qualitatively, our predictive events closely match ground truth boundaries with a coherent correspondence between visual content and textual descriptions. To conclude, Stark learns the supervised saliency from GT annotations at no extra cost and applies it to both retrieval and generation through a unified design. This leads to state-of-the-art performance on both benchmarks. Thank you for your attention. I'm happy to take any questions.